Good afternoon, Professor Yash Savda. Are you there? Professor Yash Savda?
I'm here. Can you hear me? Am I audible?
Just a second. We are getting your voice but in a very low tone.
Okay. How about now? Is it better?
Yeah, it's better.
Okay.
Okay, so welcome to this new session where we have Professor Yash Vasavada as speaker. So Professor Yash Vasavada is a professor and dean research at Dhirubhai Ambani University, Gandhinagar, Gujarat. He leads the Communications, Signal Processing and Machine Intelligence Lab, where his work focuses on statistical communication and signal processing theories. He holds PhD MS in electrical engineering with specialization in wireless communication from Virginia Tech, USA, and Bachelor of Engineering in Electronics and Communication Engineering from LD College of Engineering, Ahmedabad. With an extensive career of over 20 years at Hughes Network USA, Professor Vasavada contributed to the design, development, and deployment of GEO, MEO, and LEO satellite systems, and holds 12 US patents translating communication and DSP theories into real-world satellite applications. At Dhirubhai Ambani University, he teaches courses such as Introduction to Communication System, Advanced Digital Communication, and Next Generation Communication Systems. He has also played a central role in advancing research at the institute, serving as PI and co-PI on multiple Department of Space funded projects with support exceeding more than 1.25 crore. In 2020, he established the CSPMI lab with ISRO funding, which currently drives 5 active research projects and supports a team of 8 JRS, including MTech and PhD scholars. So, a very warm welcome to Professor Yaswa Savda. And he will be taking courses, the basics of communication, which are required in quantum communication. Over to you.
Okay. Thank you for a nice introduction. So am I audible or is my voice
Yes, you
coming
are.
now?
Yes, you are audible. You can share your screen, so it will automatically. Our sharing will stop.
Okay. Okay. So I hope my screen is visible to everybody.
Yes, screen is visible.
Okay, fine. All right. So first of all, thank you, Professor Rajendra Mitrawal, for inviting me to deliver these sessions on classical communication theory and for a nice introduction. So today's topic is information theory and basics of digital communication. Okay, so how it connects to the overall quantum computing, quantum communication. I do not know. I'm not an expert in quantum communication. But what I hope that I'll be able to do to some extent at least is to give you the classical foundation or classical counterpart to the quantum related advancements that are being researched. So today's topic is classical information theory and the basics of digital communication. Okay, so that is the topic of today. And then I'll be covering all the other topics as per the schedule that is shown here over the coming 3 days. Okay, so I think Professor Mitrawal has already described my background, so I won't spend too much time on it. Let me just give you a list of books that you may refer to. So there is a nice book by Professor Madhu. It is available online, freely downloadable. Another book is also freely downloadable and very nicely written by Professor David McKay. And then there is what is known as the classical book on digital communication by Joan Proekes. Actually, now it is in its 5th edition, not 4th anymore. And then there is another good book by Professor Leon Couch, Digital and Analog Communication. I think its edition also has incremented above and beyond 6th. So this date is, I think, a bit outdated. And then there are several other nice books. Professor Scalar has written a book on digital communication. Professor Haken has also written another book on digital communications. There is a book on error control coding, which is the noisy channel coding theorem that we will be studying later on. And similarly, a book on digital modulation coding by Wilson is another book that you may want to refer to. Okay, so
Sorry to interrupt you, but
yeah.
can we make this full screen?
Oh yeah, sure. Yeah, is this better?
Yes, perfect. Thanks.
Okay, all right. Okay, so I will provide some motivation by saying how some of the fundamental advances in this domain, in the domain of communication theory, information theory, how they happened by some very fruitful minds, mathematically sharp people who were looking at some of these topics maybe 50 to 70 years back. And they took up some of the simple things that we kind of do not often think about too much, but they investigated upon it and took it to the next level. And so a very simple problem that you would have likely solved in your high school math, that suppose if there is a factory making some device, let's say bicycles or anything else, but it is known that about 10% of those bicycles are defective, and you end up going to that factory and inspect 10 cycles made in this factory. So what is the probability that the 3 out of 10 of these cycles that you testing, they are found defective, right? So this is a simple probability question. There is really not much to it once you have the basics of probability theory worked out, and you would kind of dismiss it. But it was in fact an extension of this problem that led to maybe development of the entire field of information theory. And one of the realization that dawned on engineers and scientists once that foundational work was done was that even if you take some data which is of very tiny size, right? So today we don't think too much about data or files or anything which is maybe even several kilobits. It's only when the size of the file becomes several megabytes or nowadays even several gigabytes that we start thinking that, okay, now transferring those files over internet will be little time consuming, or storing it on our device will take a little more space. So something like, let's say, 0.1 kilobits, only 100-bit long file made up of zeros and ones, you would kind of tend to dismiss it as really not having much of import. But if you do the basic math, you realize very quickly that if you consider this binary data to be generated at random, then even a 0.1 kilobit type of data, which is 100 bits, is actually 1 out of 2 to the power 100 possible data streams, right? So there will be 2 to the power 100 possible sequences, binary sequences, out of which this one particular file that you have is drawn out of that, right? So it's already a humongous number, because the age of universe, not in maybe years or millennium, but even if you go down to picoseconds, is only 2 to the power 98, right? So 2 to the power 100 is a humongous number. So the realization is that even when we are looking at some very tiny data, it is almost like magic that we are looking at it, because it's such a rare thing for it to occur. And that is actually one of the reasons why the scientists and the engineers kind of thought about, and then they ended up developing algorithms that allow big data files with sizes in megabytes and gigabytes. So if I, let's say, consider megabyte, then this 2 to the power 100 will become 2 to the power 8 times, I don't know, 1 followed by 6 zeros. It's incomprehensibly large number. Forget about even gigabytes. So how to take such large data sizes and compress it and store it and even transmit it over, let's say, internet or over wireless links is has happened because of this realization that uh, this data that we are dealing with uh, is realized uh, as quite an improbable instance of an astonishingly large number of possibilities. And we'll be talking about this topic of data compression, also known as source coding, or also known as noiseless channel coding, as a part of this course. Another thing that I would like to highlight is that uh, as the end user of, let's say, a communication device, we do not need to think about this too much. But as an engineer, it is quite surprising to realize and actually conceptually kind of grasp that the data rate that our communication devices are able to achieve, let's say R in bits per second, is actually one side of a coin whose other side is bandwidth W in hertz and received signal power PS in watts. So it's like these are interchangeable quantities. So R and W and power, they are kind of, you can say, different facets or different sides of a single entity. And they are interchangeable in some sense. Uh, on the face of it, it doesn't seem like that should happen because R is in bits per second. What has that to do with power in watts? Right? Power is a physical quantity. It's something measurable on an instrument. And to see that is translatable to R in bits per second is quite a revelation. And so that is something that is, again, we'll talk about it in this lecture itself. And specifically, we'll see that there is an equation which says that data rate R that can be achieved by any communication device or communication link actually can never exceed the product of the bandwidth W and logarithm of 1 plus SNR, PS over PN. Okay, so that is kind of the fundamental relationship that you can say is the foundational concept as well as a limit of information theory as well as digital communication. And this also actually can be derived using the problem that we had looked at earlier. Another quite interesting thing that happens when you get down and focus your attention in studying the communication theory is that you soon realize that the type of mathematical optimization that a communication receiver does is kind of similar to what human brain does in a very natural manner. Okay, so in a way, communication theory is fundamentally kind of connected to the topic of artificial intelligence. And we will see that the theories that we will use to do symbol detection at the communication receiver actually are very closely connected to the topics of AI and ML. And if you think about it, it is not too surprising, because although we take it for granted, uh, our brains are the most expert, the the best machines, so to speak, uh, the most powerful entities in the entire world, the most efficient entities that can do communication, right? No other animal species or nothing else comes anywhere close to it. And the reason why we are able to communicate, at least partly, is that we are very good at forming beliefs and updating them. Right? Whenever we have some evidence, that immediately leads our brains to conclude on certain cause, what produced this particular effect. So the relationship between effect and cause is very naturally and effortlessly calculated by human brains. And that is one of the reasons why we are very good at communicating. And that is the reason why we can understand what somebody else is saying. We can kind of go beyond the words and get to the meaning of what the other person is trying to tell us. And that essentially is an art of detecting the intent behind the person who is communicating. And it is that particular idea which is kind of crystallized in a mathematical manner in the communication theory. So we will learn the Bayesian theory, and we will see that it kind of very nicely leads us to optimal designs of communication receiver. There are other things that are very interesting about this general topic of classical communication theory. Maybe we will not get time to touch upon all of them, but there's some linear algebraic math based on eigen analysis. They ended up kind of putting a roller, a heavy roller, or rather a wrecking ball, on billions and billions worth of USD worth of development and engineering, when the entire wireless infrastructure moved from 3G to 4G. Okay, so this happened because a technology called OFDM came about. Until 3G, it was either a combination of CDMA, TDMA, FDMA, etc. And then starting from 4G and now going on to 5G, quite likely even 6G, it is all OFDM, right? So OFDM is so different from TDMA or CDMA or FDMA that all of the infrastructure in terms of your phone, in terms of the electronics, in terms of the hardware, in terms of the firmware, in terms of the base station, all of that infrastructure had to be revamped. All of the investment that happened, all of the millions and millions of man hours that went into development of TDM or FDMA, all of that had to be kind of washed away and replaced by OFDM. I mean, nobody would like to kind of write off their investment, even if it is not billions and billions worth of USD. But still, it happened. And that kind of, again, is an indicator of the power of some highly elegant and conceptual mathematical theories. When we talk about the noisy channel coding in one of our subsequent sessions, we will realize that the algorithms and the schemes that are implemented in today's wireless devices, including your 4G or 5G phones are kind of quite similar to what your brain is trying to do when it is trying to decipher the meaning of your friend, what he or she is trying to tell you in a noisy room or over a weak phone connectivity. Or sometimes you may be looking at some words whose spelling is not correct, or maybe grammar, which is a little bit inaccurate. And then you automatically want to correct the spelling or correct the grammar. So that is the type of uh, autocorrect that your phone does at a very micro level uh, as a part of what is known as noisy channel coding. And so that is again a subject that we'll be looking at. Okay, so maybe before moving forward, let us look at several questions that the communication, whether it is classical or quantum communication, ultimately has to be about transfer of information, correct? That is typically what we mean by communication. But then what is information? How would you define information? How would you measure it? What is the way to transmit information? And a little more advanced question is, how much information can actually be received when what you are transmitting gets through a real world communication channel that can corrupt it? And we know this firsthand because whenever we are trying to uh, connect to somebody while being in a train or while being in some remote outdoor location, our phone calls don't work quite as well, or our internet connectivity doesn't hold up as much. So it has to do something with uh, the noise or the corruption or the interference that the real world communication channel is introducing. When it becomes too much, then our phone call drops, our internet connection dies. When it is not that severe, you can get something through, but not uh, as effortlessly as we would have liked. And when everything is good, then all our conversations flow without any problem. Our internet connection is fast. So there has to be some connection in terms of the noise or the interference, disturbances that the communication channel introduces versus the amount of information that the sender is trying to send. The sender might want to send a 5 gigabyte video, but if the noise is very high, then how much of it will actually get through versus when there is not much noise? So these are some of the questions that relate to this overall topic. And these questions are difficult to answer because there is a lot of subjectivity. What is highly informative for one person could be non-informative for another. And despite this subjectivities, actually, there is very nice mathematically satisfying way of defining the information, which is based on the notion of influence. And the reason why this is very pleasant and satisfying is because, in fact, this is what we intuitively understand by uh, being informed, right? When we say that I was informed by the lecture of so and so professor, what we mean is that that professor was able to influence my belief system, right? How much my existing belief system changed because of what was conveyed to me. And that is uh, the platform over which the definition of information will be built. And so with that, I'll give you one specific question. Maybe for the interest of time, we won't solve it right now. In case if somebody knows the answer to it right away, uh, you can say it, or then this becomes kind of direct for you. But Otherwise, if you have not looked at this question, it might be a little surprising. But I would like you to pay attention to the notion of influence, how much the beliefs are being changed. Now, this example is from daily life, okay? But we will see that it has a very fundamental inherent connection to the communication theory and the information theory. This question was prevalent upon all of our minds maybe 3 or 4 years back when coronavirus was uh, viral. Suppose there is a test to detect the disease, let's say a disease named C, whose prevalence is 1%, meaning that if you take a general population, 1 out of 100 people is infected by this disease. Now you go to a lab, any lab, and do the test for this disease. The problem is that no lab is 100% foolproof. There is always going to be false positive and false negative. So suppose that the test for this disease has a false positive rate of 5%, meaning that if you don't have the disease, the test will still come out positive with a probability of 0.05. And let us say that the test has a correct positive rate of 95%, meaning that if you have the disease, then there is a 95% chance that the test will say that you have the disease, meaning that when you have the disease, there is still a 5% chance that the result will come out negative, right? So this is the false positive. This is actually false negative. Both are, let's say, 5%, right? You don't have the disease, the test will, with 5% chance, will say that you have the disease. And if you have the disease, there is a 5% chance that the test will say you do not have the disease. So you take the test and the test result comes out positive. What is the probability that you actually have this particular disease? That is the question here. Any thought?
Actually, participants will not be able to respond
Oh, okay.
because they are muted.
Okay, fine.
Maybe they can post for answers on chat window. If you ask,
Yeah.
they will be able to answer on chat window.
Yeah, if you have some initial uh, uh, guess as to what would be the probability of the person having the disease when the test result comes out positive, you can put it on the chat window. Okay, so this is the question is that given this particular setup, what is the probability that when you take the test and it comes out positive, you actually have the disease? And so somebody said close to 100%, somebody said almost 95%. Yeah, so 95% seems to be kind of the answer, right? So it actually turns out that the correct answer is that in this particular case, you go and take the test and the test result comes out positive. The probability that you actually have the disease is still only about 16%. Okay, so it kind of defies our intuition. And the way to think about this is that this particular problem which I mentioned belongs to a generic communication channel where the information is being transmitted from the world of causes to the world of effects. Okay, so what is the world of causes? This is the underlying bodily situation. Somebody has the disease, which is represented by C equal to 1. or doesn't have the disease, which is C equal to 0. Unfortunately, we never have direct contact with this world. Okay. What we actually observe is the world of effects. This is the outcome of our laboratory test. T equal to 0 means the test came out negative. T equal to 1 means test came out positive. Now, the connection from C to T is through this green and the red lines. And that is what we will call as the communication channel over which the information transfer happens. Correct. Sudarshan gave the right answer, 16%. So what this communication channel says is that if suppose those red colored cross connections were not present, then every time C is 0, the disease is not there, the test will come out to be 0. When the disease is present, C equal to 1, the test will also say that the disease is present, T is equal to 1. But in real world, there is always going to be some cross connection. In our case, P error 0 was 5%, P error 1 was 5%. And because of that, when you get T equal to 0, you cannot be absolutely sure that C is equal to 0. C could actually be 1. And then through this P error 1 connection, you got T equal to 0. In the word, in the Bayesian math, the probabilities on the C are called prior probabilities. They are defining the probability distribution of the various causes. So in our case, the prior was Q was 0.01, 1 minus Q was 0.99. So prior was heavily skewed towards C equal to 0. All of these other variables, P error 0, P error 1, they are called likelihood function. And so that is defining the quality of the communication channel. If the communication channel is good, then P error 0 and P error 1 are going to be small. If the communication channel is bad, then P error 0, P error 1 will become higher. And then PT is called the evidence, which is what we observe. In the context of a communication channel, the world of causes becomes the transmitter and world of effects becomes the receiver. So when you are talking to somebody on your phone and you are listening to what they are saying, you are at world of effects. Person is at the world of causes. The transmitter is always C and the receiver is always at T. And the receiver, having observed T values, you are trying to figure out what C values are. But you don't know what C values are for sure unless this P error 0 and P error 1 are 0. And in the context of communication theory, we always have to deal with situations where this P error 1, P error 0 are non-zero. And so having observed T equal to 0, we have to figure out whether C equal to 0 is more likely or C equal to 1 is more likely. We have to kind of go back on this connections. And that actually leads to a very basic but very powerful model of a communication channel called binary symmetric channel, which we will look at on the next page. It's a binary because it works only on the bits, zeros and ones. Symmetric because we are making P error 0 and P error 1 to be equal. So there is a symmetry. It doesn't matter whether bit 0 or bit 1 was transmitted by the transmitter. And that P error 0, P error 1, they both are same. We call it just P, and that channel becomes BSCP. So this is how it looks like. Binary symmetric channel. When you get Y equal to 0, it could have been caused with probability 1 minus P when the transmitter sent X equal to 0, or Y equal to 1 when X equal to 1 was sent with probability of 1 minus P. Again, this is X is the world of causes, Y is the world of effects. X is the transmit, Y is the receive. The job of the receiver is after receiving a bit 0 or bit 1 to figure out whether X was 0 or X equal to 1. There is another model that is useful that we will look at. It's called binary eraser channel, where the bits are transmitted bits are obviously again zeros and ones, but the receiver can get either 0, 1 or eraser, meaning it doesn't get anything. And when X is equal to 0 transmitted with probability of P, that bits get erased. And with the probability of 1 minus P, the bit comes through without any defect. Same with the situation when bit X equal to 1 is transmitted. Okay, so this is kind of another mathematical model of binary data transmission. They seem to be simple, but they are very powerful because, as we know today, all of our communication mechanisms are happening by exchanging bits ultimately, right? Even our voice calls, when we use, let's say, VoLTE, voice over LTE, our speech is kind of getting digitized and then converted into bits. All of our data connections, emails or Instagram or WhatsApp, everything is ultimately being transmitted, being exchanged, where the basic currency is bits. And therefore, these models are quite powerful because they kind of go to the essence of the problem. What happens at the individual bit level? How many bits are getting corrupted? If P is 10%, it means that maybe on average, let's say 10 out of 100 bits that you transmit, zeros will turn into 1, 1 will turn into 0. On the other hand, in this case, out of 100 bits that you transmit, 10 will get erased and the remaining 90 will come out correct. Over here, the bits are getting flipped. 1 is flipped into 0, 0 is flipped into 1, which is what is happening in this coronavirus problem. You don't have the disease, but the faulty test equipment says that you have the disease. Or you actually have the disease, but the equipment says that you don't have the disease. So that's very similar to what is happening with BSC. Whereas with BEC, you don't have to worry about bit flips. 0 never gets confused as 1 at the receiver. But erasers happen. So if you're getting sequence of bits, suddenly you get something which you can't see whether it is 0 or 1. It's just blank. So that is the model of binary eraser channel. Okay. So I think maybe some of you already solved this question. Yeah, so maybe you can take up this problem of coronavirus disease detection that I gave you and try to solve for this question that suppose the observed value of y is 0, then what is the conditional probability that x is equal to 0 versus x is equal to 1? Meaning that you took the test came out negative, then what is the probability that you don't have the disease versus you have the disease? Similarly, you can repeat this when y is equal to 1. You took the test came out positive. What is the probability that you have the disease versus you don't have the disease? And this is the type of problem that a mathematician called Claude Shannon was busy solving about 75 years back. And he really developed a whole theory of information out of it. And what was amazing about his work was that this entire development was done entirely by himself. The whole theory of information, quantification, definition, uh, was the work of a single mind. And another good thing is that if you actually do take up the paper written by Shannon, it is, by the way, the highest cited paper in the engineering math literature. It is very nice to read. You don't have to really uh, know some very advanced topics of mathematics to make sense of what Shannon did. And we will look at Shannon's thought process, the what the engineers and the scientists find amazing today after 75 years of that work is that uh, the foundational derivation that was done in that 1948 paper by Shannon kind of puts a limit on what a communication system can ever achieve, whether it is 3G, 4G, 5G, 6G, whether you use CDMA, TDMA, FDMA, or FDM, doesn't matter. It provides a foundational limit. And that limit was crystallized by Shannon by formulating a very simple but conceptually very powerful model of what a communication system does. And if you look at it, this actually is very much relatable to us humans, because this is what we do, in fact, when we communicate. Even person to person communication, verbal communication, without involving any electronics, right? What do we do when we communicate? We have some things in our mind, right? So this a set of messages is this particular block. And these circles that I have drawn are maybe different things that we have in our mind. Maybe we want to compliment somebody, maybe we are angry at somebody, maybe we want to make a logical point, something, right? Whenever we are talking to somebody, we have something that we want to say. That particular thing is actually not made up of words or letters or language at all. It's entirely something which is in our mind. But we select that particular uh, entity, that particular topic, out of many other things that could possibly be brewing in our mind at any particular point of time. We select that. And what Shannon said is that that act of selection itself is the primary reason for generation of information. What you select is what drives the information. And that selection is done over what type of set? Is that set very small, very big? And how frequently you are selecting, right? So that is one part of, or rather the generative part of an information. And then what information source does is, after selecting that particular message, it converts it into a signal. And that conversion happens by a communication transmitter. You can think of the communication transmitter as your brain or your vocal auditory system. Your brain actually, one part of your brain picks up a particular thing that it wants to relate to or convey, and the other part of brain converts that into your actual speech signal. Or if you're writing, it could be your alphabetic sequence, something which is tangible, something which is measurable. That is the goal of a communication transmitter. What Shannon said is that that signal invariably goes through some noise. You are speaking, but maybe there is some loudspeaker playing in the background. So what you are saying will not be heard without any disturbance at the receiver. The goal of the receiver is exactly the opposite. It takes this physical signal, which may have been corrupted with noise, and its job is to convert it back to this formless, symbol-less meaning, something which is abstract. But as long as that abstracted realization is same as what the transmitter had in mind, then the receiver in their mind gets the same meaning which transmitter wanted to convey. So that is why I have deliberately picked that the transmitter has selected the second circle, and because the noise probably was not very large, and so communication receiver converted the physically received signal into that abstract entity which was also second. So now we can say that communication has happened effectively or efficiently or accurately. If suppose the arrow went to the first one or the third one or the last one, then we would say that, well, transmitter had something to say, but the receiver kind of got an entirely different meaning and the communication broke apart. Or the transmitter had one particular set of messages, the receiver didn't even have that set of messages. And so receiver got the signal, but it couldn't do anything with it. You are speaking in Hindi, but the receiver only knows Chinese. Well, then anything that you are saying cannot be meaningfully interpreted because this particular scheme is not there in the receiver's brain. In the context of communication technology, this is actually what is happening. Communication transmitter is your phone. Communication receiver is also your phone or any other communication device. And the information is being exchanged exactly in the similar manner. Shannon crystallized that the key design parameters are size m of the SAT, which determines the number of bits that you need, log base 2 of m bits, and how many messages you are selecting, let's say every second. That will determine the number of bits per second that you need to transmit these messages. Power PS that the communication receiver gets. So this is the power PS at the receiver, and the power of the noise at the communication receiver, that is PN. And so based on, and also the bandwidth over which these messages are exchanged. And as I said earlier, Shannon formulated this fundamental equation that R can never be greater than W times log base 2 of 1 plus PS over PN, bits per second. It is also written as eta B less than or equal to log base 2 of 1 plus gamma. Eta B is R divided by W, and gamma is PS over PN. Gamma is SNR. R divided by W, eta B is called spectral efficiency. So I'm plotting that here. X-axis is gamma, and the y-axis is spectral efficiency. What is spectral efficiency? Eta B is R divided by W. What is R? Data rate in bits per second. What is W? Hertz. So what is eta B? Bits per second per hertz. If you have 1 hertz of bandwidth, how many bits per second you are transmitting through that 1 hertz? If you are transmitting 1 bits per second per 1 hertz, you are over here in terms of spectral efficiency. If suppose you are transmitting 5 bits per second for each 1 hertz of bandwidth, then you are spectrally far more efficient. You are needing the same unit of bandwidth, but you are transmitting larger number of bits per second. So it's all obviously good to be going up on the y-axis, because you all obviously want to be able to transmit more bits per second for each unit of bandwidth in hertz that you have. The problem is that in order to go up on y-axis, you have to go rightward on the x-axis, which is gamma. The problem with going rightward on x-axis is that you have to increase PS over PN. Now suppose that PN is something that you cannot control. It is coming, the power of the noise is something related to the communication environment, and you can't control it. It is what it is. Then to increase gamma, you will have to increase PS. The problem with increasing PS is that you will need bigger power amplifier, you will need bigger antenna, you will need bigger battery, and also all of that will lead to an inefficient operation. Okay, so that is what this slide says, that R over W is one critical parameter, which is called spectral efficiency. PS over PN is another critical parameter, which is called energy efficiency. And energy efficiency and spectral efficiency are kind of at odds with each other. An increase in spectral efficiency means that you have to accept a decrease in energy efficiency and vice versa. For example, we will see that there is a scheme called binary modulation, which uses only 1 bit per use of the channel. In contrast, Emery modulation sends multiple bits. So compared to binary, Emery modulation is spectrally more efficient, eta B is greater. But if you use Emery modulation, then you have to have greater SNR for the same performance, which means that you have a smaller energy efficiency. Okay, so that is the main concept of spectral efficiency and energy efficiency. Another thing that this equation tells us is what I said, that the bandwidth efficiency and energy efficiency kind of can be traded off, just like power and bandwidth can be traded off. If you have more power, then you can live with a smaller bandwidth. Or if you have small power, then you can increase the bandwidth and still attain the same data rate, right? So that is why, just like Einstein's equation E equal to mc squared showed that energy and mass are kind of convertible, this equation says that the overall data rate achieved is a function of W and PS. If W is less, you can increase PS. If PS is less, you can increase W. You will still get the same R, right? So that is what we are saying here, that power and bandwidth can be kind of exchanged with each other. Okay, I think I am almost out of time. I'll just quickly wrap up. Next few slides I will very quickly go over. Apart from its connection to the quantum communication, the reason why this topic is interesting is because most of the development that is happening in the world today is not in quantum communication. It is in the classical communication, 4G, 5G, 6G, etc. And there are lots and lots of different vision statements that engineers and industrialists have, where very advanced communication technologies will be brought to bear to solve some real life applications such as high-speed mobility, massive IoT, broadband access in dense areas, broadband access everywhere, even when you are, let's say, traveling in a train and the train is in between two villages, you'll still get broadband connection, ultra reliable connection, robotic surgery, etc. So this is again the type of vision statement that 4G and 5G systems have to achieve hologramic communication, to achieve very precise communication for military applications, for robotics, right? Vehicular communication, autonomous vehicles, etc. And so that is the reason why this topic is highly pertinent to today's times. And then finally, let me just go over some block diagrams that we will be studying in further detail in the coming sessions. So this is a very general diagram of a digital communication system. There is an information source. By the way, this is an extended version of the conceptual diagram that I had shown, that Shannon had developed, right? This one. This is conceptually a complete diagram, but engineering design wise, this is how it got implemented in today's technologies. Information source is source encoding or noiseless channel coding, noisy channel coding or channel encoding, modulation, and then RF up conversion and transmission through an antenna. The transmitted signal goes through the channel, which can introduce noise and other types of disturbances. And the output of the channel goes through the inverse functions at the receiver. This is not an abstract drawing, although it may look like that. To show you that, I have taken here the block diagram of a real world communication system that has been implemented. And you will see that it is showing the same blocks that I have shown here. This is another such diagram, maybe with slightly more details, but the conceptual blocks are identical. Source encoding, channel encoding, etc. Okay, so that I think is the summary of what I wanted to say in today's introductory lecture. And I think I will conclude here today. And then we will take up the next topic when we meet tomorrow.
Okay, so any questions from participants? So generally, if participants have questions, they post it on the chat box, but I don't think anyone has any questions from today's session. Yash, are you there?
Oh, yeah, I'm here.
So, I mean, there is just one question which somebody is asking regarding some basic book which they can refer. If you just suggest one single book.
Actually, I have given a list of books, but the one book that I would suggest is the one by Upmanyu Madhav, Introduction to Communication Systems. And as I said, it is freely downloadable. And it's also a very nicely written book. So I would suggest that book to begin
Okay.
with.
All right. There is one more question, but I don't think so. Basically, the question is, what is the difference between classical and quantum communication? So basically, these sessions are related to classical communication. Probably we can keep this question for the other speakers who would be discussing quantum information theory after Professor Yash Vasavada. So probably from next week onwards, we'll start with quantum information theory. Probably at that time, this question may be answered by the other speakers.
Yeah, I think the purpose, as I see, of these sessions is to kind of clarify, make it very clear in your minds what the conventional communication system and what the classical information theory is, right? Once you have that very clearly identified and you are very crisp about that, then it will become very natural for you to understand what differences are brought in by quantum communication. So let
Right.
us not go to what the difference is at this point of time, because to describe that, we have to first know exactly what the classical method is, right? And we have not completed that. So I suggest that, well, let us not get into that today, but keep our focus on understanding the classical communication and the classical information theory.
Okay, so I have already posted the material, the slides of Professor Yaswaswara on Canvas. You can see the first PPT related to today's session is already there. And in his slides, you can see the list of all the reference books which he was talking about. So in case if you want to refer them again, you can go to Canvas and look at the first PPT. There are slides related to the reference material already there. All right, so thank you, Professor Yash Vasavada. We will continue with the remaining sessions from tomorrow onwards. Thanks once again.
Okay, thank you. Bye.
Bye.